In this class, we are going to discuss the construction and working of Michelson interferometer designed by Michelson. This interferometer is used to study interference pattern of light, and we can calculate wavelength of the light. For any transparent medium, we can calculate thickness of the transparent medium and its refractive index also. In this class, we will discuss the construction and working of this interferometer. Let us observe what apparatus are required to arrange or to design this interferometer. Here we have the list of the apparatus. We have two mirrors, plane mirrors, and we denote these two mirrors with M1 and M2. They are of equal size, and these two mirrors are arranged such that M1 mirror, we denote that mirror, first mirror with M1, it can be moved, and M2 mirror is the second mirror, it is fixed. And the second one is we need a glass plate G1, but this glass plate is half silvered glass plate. It means it is partially silvered on one surface of the glass plate, and so that when light incident on this glass plate, after transmitting into the glass plate, the light is split into two parts at the half silver surface. One part is reflected and the other part is transmitted through the glass plate. And the second one is we need one more glass plate, compensating glass plate. We denote with a G2. These two glass plates, G1 and G2, are having the same size. But the only thing is G1 glass plate is half silver glass plate, but G2 glass plate is a normal glass plate which is having equal size. And we need a monochromatic source of light which emits a single wavelength, it means single color, and instead of this monochromatic light we can use a laser light also. And we need a traveling microscope. We denote this microscope with a letter T for observing the interference pattern. Okay, let us see what's the construction of Michelson interferometer. Here we have the schematic diagram which represents the arrangement of the all apparatus in Michelson interferometer. So as we said, we need two mirrors M1 and M2. These two mirrors are exactly perpendicular to each other. The reflecting surfaces of the two mirrors are exactly perpendicular to each other. So we arrange this mirror M1 along the x-axis and this mirror M2 is arranged along the y-axis. So these two mirrors are perpendicular to each other, and the next thing is this M1 can be moved here with the help of a screw. So it can be moved on a beam here. Here we have the scale here, we can see this one. So this is the scale. On this scale it can be moved, and this mirror M2 is fixed here. And this half silver glass plate G1, here this is G1, which is arranged exactly 45 degrees relative to this mirror M2, and it is placed in front of the glass plate M2. And monochromatic source of light, here we have the monochromatic source of light which emits a single wavelength. It is arranged exactly in front of the half silvered glass plate G1, and we need a collimator, a convex lens, for making this light which is coming from source of light into a narrow beam of light. Another glass plate G2, a plain glass plate, normal glass plate, is arranged in between the half silvered glass plate G1 and mirror M12. And this traveling microscope is arranged here to observe the interference pattern. This is the arrangement of Michelson interferometer. Two plane mirrors are constructed perpendicular to each other. M1 is moved on the scale and M2 can be fixed. G1 is arranged in front of M2 at 45 degrees relative to M2, and G2 mirror glass plate is arranged between G1 and M2. The source of light is arranged in front of the glass plate G1, and we can arrange at the traveling microscope. Here we have the traveling microscope. So let us see what's the working of Michelson interferometer. When this light coming from the source S, passing through this collimator or a convex lens L here, it is made into a narrow beam of light. So this narrow beam of light is traveling towards the glass plate G1 and strikes the glass plate G1 here and transmits into the glass plate G1. So when this light strikes this half silver surface of the glass plate, it splits into two parts. One part is moving upward towards the mirror M1 after reflecting from the half silver surface. The second part is moving towards mirror M2. So this mirror M2 is fixed here. We have one other glass plate G2. This light traveling through G2 strikes the mirror M2 and it incidents the mirror M2 normally, so it is reflected back from the mirror M2. And again after traveling through the G2 glass plate and strikes this G1 and reflected downwards here. This is about the light which is traveling towards mirror M2. And what about the light which is traveling towards the mirror M1? This light which is traveling towards the mirror M1 here, it already traveled through the glass plate G1 once and reflected at the back surface, half silver surface of the G1 and traveling towards M1. After incidenting on M1 mirror, the light is again reflected back in the same direction, opposite direction, and this light again here travels into the glass plate here and downwards reflect transmitted here. So this light which is traveling towards M1 travels through the glass plate G1 three times. Number one, so when the light is coming from the source S1, it travels through G1 and reflected at this surface and reflected towards the mirror M1. And again here, when it is reflected towards the mirror M1, again it travels through the glass plate G1, so two times. And again after reflecting from mirror M1, it travels downwards, then this is the third time. So this light travels through glass plate G1 three times, but this light which is traveling towards M2 travels only one time. So we have to compensate that path uh, between two lights. So we need this glass plate G2. We arrange this glass plate G2 in between G1 and M1 to compensate the path difference between two lights. Here we have two reflected lights which are traveling towards the microscope T here. These two lights are are formed or produced due to the division of amplitude. So this reflection is the division of amplitude and the interference is produced by the division of amplitude of the light. So we can observe the interference pattern through this micrometer T here. So this is how this interferometer works and interference pattern is produced. And let us say what is the interference pattern using this Michelson interferometer. Here we have two types of interference patterns. Number one, circular fringes, and number two is localizer fringes. So what does it mean by circular fringes here? This type of fringes are produced when the two mirrors are exactly perpendicular to each other. So here when you see through this microscope, we can see the mirror M2 through this microscope. Here this is mirror M1, we can see the mirror M1. At the same time we can see the virtual image of M2 also. So when you see the virtual image of M2, if the two mirrors are exactly perpendicular to each other, then virtual image of M2 we denote with this M2 dash, and the mirror M1 both are coinciding with each other. So when the virtual mirror of M2 coincides with mirror M1, when it is observed through the traveling microscope, then the two mirrors are exactly perpendicular to each other, and we have this type of pattern which is circular fringes. These circular fringes are concentric circles, and at the center we have a dark central minimum which is surrounded by bright and dark circular fringes. We can move this mirror M1 and we can cross the dark circles and bright circles of this interference pattern. So circular fringes are formed when both mirrors are perpendicular to each other and mirror M1 exactly coincides with virtual image of M2. And the second type of fringes is localized fringes. This type of fringes are formed when the two mirrors are not exactly perpendicular to each other. As I said, mirror M1 can be moved on the scale. So when you observe through the traveling microscope, mirror M1 can be seen at the same time the virtual image of M2 is also seen. The virtual image of M2 is denoted by M2 dash. It may be below the mirror M1 or above the mirror M1, or it can intersect the mirror M1. So depending upon the position of virtual image of M2, we have three types of circular fringes. Here we have three types of circular fringes in this diagram. So this is here we have in the first diagram the circular fringes are replaced by semicircular fringes. These are the semicircular fringes. So these semicircular fringes are formed when the virtual image of M2 is below the mirror M1. So the semicircular fringes are curved towards right side. And we have this third diagram when this virtual image of M2 dash, that is virtual image of M2, we denote with M2 dash, is above the mirror M1. Then we have the same semicircular fringes but turned towards left side. So semicircular fringes are formed when the virtual image of M2 is either above or below the mirror M1. And third type of fringes is straight parallel fringes. These type fringes are straight and parallel to each other. This type of pattern is observed when the virtual image of M2 intersects with M1, mirror M1. The two image and the mirror M1 intersect with each other, then we can have this type of straight parallel lines. So these fringes which are semicircular and straight parallel lines are called localized fringes. So we can have these many types of fringes. One circular fringes, the second one is localized fringes which are semicircular, either left side or right side turned, and also straight parallel line fringes. So this is about how we can produce interference pattern using Michelson interferometer.